I welcome you all for this lecture series on artificial intelligence and machine learning. In this lecture, we will briefly discuss about the topic probabilistic discriminative models. First, we should know why should we learn this probabilistic discriminative models. Learning probabilistic discriminative models is essential for anyone studying artificial intelligence and machine learning, that is AML, because these models focus on directly estimating the conditional probability P of y given x, which is crucial for making accurate predictions and classifications. Unlike generative models, which try to model the entire data distribution, discriminative models concentrate on the decision boundary between classes, leading to higher predictive performance in many real world applications like speech recognition, medical diagnosis, and image classification. Mastering these models, such as logistic regression, SVMs, and neural networks, equips AIML learners with the ability to design systems that are both efficient and highly accurate in recognizing patterns and making the decisions. We'll see one by one. First, we'll see the introduction to probabilistic discriminative models. We'll see the definition. The probabilistic discriminative models are designed to directly estimate the conditional probability, that is, probability of P of y given x, where y represents the class label and x represents the feature vector. These models focus on learning the boundary between different classes without making any assumptions about distribution of the input feature themselves. This makes discriminative models particularly powerful in classification tasks as they aim to minimize the error in classifying data points based on observed data features rather than modeling the underlying data distribution. The main objective of this function is the primary goal of the discriminative model is to learn the relationship between input feature x and the output feature y by modeling the conditional probability of p of y given x. By focusing on the decision boundary between classes, these models seeks to directly map features to class labels. This is in contrast to generative models, which will also model the joint distribution, that is p of x comma y. Discriminative models typically lead to better performance in classification tasks because they do not attempt to model the distributions of x, which can be complex and unnecessarily for the task at hand. Next, logistic regression, that is a discriminative model. This is the model equation. Logistic regression is one of the most fundamental probabilistic discriminative models used for binary classification. So this logistic regression is mainly used for classifying the binary variables. It models the conditional probability P of y is equal to 1 given x, and using the logistic function, how we are going to write the here what it represents, the probability that the label y is equal to 1 given the feature vector x. The model uses the logistic sigmoidal function to output a probability value between 0 and 1. This is given by probability of y is equal to 1 given x is equal to 1 divided by 1 plus e power w to the power w transpose x. Here, that is here the w is the vector of the model and x is the future vector, that is input x1, x2, x3, and this is the weight vector. And the function w transpose x represents the linear combination of the input feature. For example, n number of inputs are coming, each input vector is associated with the weight value that we'll discuss in the later lectures. And this function we are calling it as the sigmoidal function. The sigmoidal function squashes this linear combination into a probability range between, it will gives us the value always between 0 and 1. So that only we are calling it as it is used for the binary values. So this logistic regression model gives us probability values of clash for 1. To predict the label, we typically use the threshold. Commonly, let us say if you are taking 0.5, in this case, if this value is greater than 0.5, the model predicts the class 1. Otherwise, it will give us the 0 probability. That if I am fixing the threshold value is 0.5, the value of this value, the probability is less than 0.5, it will be classifying the value as the output as 0. Otherwise, the output as the 1. Next, maximum likelihood estimation, that is MLE, maximum likelihood estimation, MLE for logistic regression. And this MLE for logistic regression, how it is being used? In logistic regression, the model parameters model parameter W means what? Weight, are learned using maximum likelihood estimation. Here, learning will be taking place in this probability discriminative models. The idea is to find the parameters that maximize the likelihood of observing the training data. The log likelihood functions for logistic regression is expressed as L of W, logistic function L of W is equal to summation I is equal to 1 or yi into log of P into yi is equal to 1 given xi plus other value is 1 minus yi into log 1 minus P of y, this value. Uh, So we are getting this equation. Here n is the number of, in this case, n is the number of data points and yi is the label for ith data point, and this xi. Xi means what? Feature vector, that is input vectors. And in this case, feature vectors. So the log likelihood function is the sum of the log probabilities for each data point. We maximize this function by adjusting the weights W to make the predicted probabilities as close as possible to the truth tables. The optimization of this function is typically done using gradient descent or other optimization algorithm. Here we have to optimize the things. Next is support vector machines, SVMs. Support vector machines are powerful discriminative classifiers that aims to find the hyperplane that best separates the data points of different classes in the feature space. SVM works by maximizing the margin, which is the distance between the decision boundary hyperplane and the closest data points from the each class, known as subtotal vectors. The hyperplane that maximizes this margin is considered the optimal hyperplane. And here the objective function we have to see, the optimization problem in SVM can be formulated as here the optimization problem for SVM is formulated as minimum of W comma P half mod of W square, that is norm square, we can call it as norm, and subject to the constraint yi is the output. This is the weight vector is multiplied with the xi, and b is the bias. So yi into w transpose xi plus b greater than or equal to 1 for all I. This value should be greater than or equal to 1 for all I, where here this w is the weight vector, and b is the bias. This xi means what? Feature vector for ith training sample, and yi is the label, that is output, right? So the goal is to maximize the magnitude of the weight vector, and which correspond to maximize the margin between support vectors and the decision boundary. That is decision boundary. The constraints ensures that the data points are correctly classified with the margins of at least one from the hyperplane. Next, conditional random filter. This we are calling it as the CRF. So all these techniques comes under what? Probabilistic discriminative models, SVM, maximum likelihood, and conditional random field, CRF. Just we'll see the overview. Conditional random field, CRFs, are a type of discriminative model used for structured prediction, particularly when the output is a sequence or has dependencies between elements. In contrast to models that predict labels independently, Like logistic regression, CRFs model the conditional probability of an entire sequence of labels given the input sequence. They are commonly used in tasks such as sequence labeling, part of speech tagging, and named entire entity recognition. And here the CRF equation, what do you mean by CRF? Conditional random field is given by the probability of y given x is equal to 1 by zx into expectation of e to the power, not expectation, e to the power summation lambda x fk yi comma yi minus 1 comma xi. What is y? This capital Y is the sequence of label, capital X is the sequence of input feature. Always this X represents the input features. And fk of yi comma yi minus 1 xi is the feature function that captures dependencies between the current and this is current and this is the previous label as well as the input features. And this lambda k are the learned parameters, and finally, the z of x, it represents what is the normalization factor, ensuring the probabilities sum to 1. So always if you are calculating the probability based theory, we have to find out the value between 0 and 1. And if you are summing up all the values, we have to get the values, the total probability value is the 1. This is the formula. Next, neural networks as discriminative models. This neural network will be separately studying in the future lectures. Neural network can also be viewed as the discriminative models when used for classification tasks. In neural networks, the input is X. Input X are processed through multiple layers of neurons, and the output layer produces the predicted probabilities for each class. Neural networks are especially powerful when dealing with complex, high dimensional data like images, audio, and text, as they can model nonlinear relationship between inputs and outputs. So in this we are using the softmax functions also. For multi-class classification, the neural network output layer typically uses the softmax function to convert. What is the function of using the softmax? To convert the raw output into proper probability values. The softmax function is given by probability of y is equal to k given x is equal to e to the power wkt transpose x divided by summation of j is equal to 1 to k e power the same wj transpose x, where here the k represents what? This capital K is the number of classes, wk is the weight vector for each class k, and x is the input vector. So the softmax function normalizes the raw output scores so that they sum to so that they sum to 1, allowing the model to interpret the output as probability distribution over the possible classes. Next, coming into the advantages of probabilistic discriminative model. The key advantages of these models are focus on decision boundary. The probabilistic discriminative models are highly effective tasks where the goal is classify and predict labels based on the input features. These models focus on the decision boundary between the classes, which often lead to better performance in classification tasks, especially when the classes are not well separated by simple distributions. Discriminative models like logistic regression, SVM, and neural networks can handle complex high dimensional data and often outperform generative models when the primary task is classification. Additionally, these models are computationally more efficient because they do not require the modeling of underlying data distribution. So, the main focus on decision boundary, better performance in classification, and it is flexible for the complex data. So, next, coming into the summary, what are all the key takeaways of this model? Probabilistic discriminative models, including regression, SVM, and CRFs and neural networks, are powerful tools for classification tasks. These models directly estimate the conditional probability of y given x without making assumptions about the distributions of the input features. And by focusing on learning the decision boundary between classes, they often deliver better performance, particularly when the underlying data distributions are complex or unknown. Discriminative models are widely used in practical machine learning applications due to their flexibility, efficiency, and ability to handle high dimensional and nonlinear data. So, coming into the conclusion, the probabilistic discriminative models are powerful tools for learning direct mapping from inputs to outputs. They offer high accuracy by focusing purely on decision boundaries rather than modeling the full data distribution. Understanding these models are important for solving real world AIML problems effectively. And mastery of discriminative models builds a strong foundation for advanced machine learning applications. So, hope all you have thoroughly enjoyed this lecture and gained valuable insights into probabilistic discriminative models. Understanding these concepts is key to mastering classification tasks in AML, as I've said already. Keep exploring and practicing to strengthen your skills further. Thank you for your active participation and enthusiasm. Thank you.